And we're back. This is video number 2. I've tried to calm myself down a little bit. Maybe the energy was a little too high in that first video. Calming down. No promises, though. When you have a piecewise function, this really helps illustrate exactly what continuity is. All right? In order for a function to be continuous at a point, its actual definition looks like this. In order for the function f of x to be continuous, and here's the thing, like, I know I got two polynomials representing a piecewise function, which means that it's continuous everywhere for x minus 1, and it's continuous everywhere for 3x minus 7. However, what is happening when it splits off into this new function at 3? 3 is like this schism where we're like, is it just a hole? Is it a spot where they both meet up? Is it not an asymptote? Is it a break in the graph? That's really what we're trying to figure out here. So it's really not continuity for the whole thing. Is it continuous at that specific value? In order for f of x to be continuous at x equals 3, these are the three things that have to happen. 1, the limit, or maybe it's 2. Let me just map it out for you. The limit as x approaches 3 from the left. I'm talking about limits. I said it's continuity today, but continuity and limits are super, super connected. Of f of x, all right, the limit as x approaches 3 from the left must equal the limit as x approaches 3 from the right. So we're basically saying the limit must exist. And it must exist at that value. It can't just be a random hole in the graph. The hole needs to be filled in, which means that those two y values, remember, a limit is just a y value, must equal the function at that particular point. This must be true. So here's how we do it. From the left, we are talking about x minus 1. Because this is x is less than or equal to 3, we're talking about everything to the left of 3 is x minus 1. So since there's no domain issue for x minus 1, we can just plug 3 in. So from the left, that might be helpful. 2. All right, 2 is the magic number. Okay. What is the limit as x approaches 3 from the right? Well, you're using 3x minus 7, because this one is indicating right endpoint behavior. So it's 3, all right, 3x minus 7, times x, which is in this case 3 minus 7. 9 minus 7 is 2. Oh, we got it. Or at least we got the first 2 at least. The limit exists, and the limit equals 2. Now, what is f of 3? Well, here's the dead giveaway. The equal to part. The equal to part states that it's not just does it approach this open hole at the y value 2 when x approaches 3. It's when it's equal to 3, it equals 2. So f of 3 also equals 2 based on this little equal to part right there. So, okay, we did all these calculations. In order for f of x to be continuous at 3, this must be true. Hey, that is true, which means it's continuous at x equals 3. And it's continuous from the left because it's a polynomial. And it's continuous to the right because it's a polynomial. So that means it's continuous everywhere. Everywhere. Oh boy. So here's kind of a shortcut now that you can use. Did you notice that all I did was plug in numbers? I basically said, hey, plug in 3 right here, plug in 3 right here. They match up. Okay, does it exist there? Yes, indeed it does, because there's an equal to. I can kind of do that up here. But it's so important that you understand that we're actually computing limits when you're trying to determine continuity. So, plug in the limit from, in this case, that's the right. The limit as x approaches 0 from the right is equal to 0 squared, which is 0. The limit as x approaches 0 from the left would be the bottom in this case, which is 0 minus 2. It's negative 2. So that instantly says it's not continuous everywhere. It's okay because t squared is a polynomial and t minus 2 is a polynomial. It's only 0 where we have a problem. So it's discontinuous at t equals 0. The question is it removable or is it non-removably discontinuous? And here's the thing. Non-removable discontinuities are ones in which the limit does not exist. The limit exists if these two match up. The limit does not exist here. In fact, let me just draw a quick graph of this for you. I don't expect you guys to do it, but just recognize that there's some real logic here. Here's t squared, only if I graph greater than or equal to 0. Here's t minus 2 if I only graph less than 0. That's an open circle right there. It's hard to see it on the video. And that made it worse. There? Yeah. All right, down 1, left 1. When I graph it and we actually look at finding limits, it's kind of obvious, like, oh yeah, that's non-removable discontinuity. There's a break in the graph. They don't match up to a specific point. Pretty much when a piecewise limit doesn't match up the left and the right, then you know it's non-removably discontinuous all the way. All right. I also included the dreaded example with the not equal to t. Oh, these just seem to be the bane of every pre-calculus student's existence because they just don't know how to properly visualize this. But you guys will be different. By the way, I didn't even mess with t like of 0 because since the limit from the left didn't match the right, I didn't have to. All right, if you'll recall from a previous video when we talked about limits, if you got a piecewise function that doesn't have like greater than or less than the number in question, but it's just not equal to, that means that your function x squared minus 2x plus 1 is basically the entire function for the whole graph, except at the point 3. At the point x equals 3, it's taking on the behavior of something completely different. So that means the limit from the left and the limit from the right are the same thing. Here, let me go ahead and graph this again for you. X squared minus 2x plus 1 is actually, if I put it in vertex form, shifted right 1 and looks like this. Where this right here is an open circle. That's what x squared minus 2x plus 1 looks like. It's a parabola with a hole at x equals 0. So really, it's like I'm not plugging these into two separate entities. This is me plugging in 3 into that polynomial and getting the value of 9 minus 6, which is 3 plus 1, 4. It's the same thing from the right. I'm using 3 squared minus 2 times 3 plus 1 for this bottom one as well. So the limits equal each other. Yes, but in this case, h of 3 doesn't equal 4. It's an open circle right there. It equals 7. 5, 6, 7. It's, heartbreaking. What that means is that it did not check off the list the 3 twins that need to happen. And these all need to be the same. But as you can see, it's not non-removably discontinuous. It's still a removable discontinuity because the limit exists. The limit exists. The left and the right match up. So in this particular case, you would say it is removably discontinuous at x equals 3. By the way, when you're talking about the final discontinuity, don't start like incorporating these numbers. I see a lot of students that'll do that when they don't know what they're doing. These are just pointers to show us like, oh, is it removable? Is it non-removable? Is it continuous everywhere? I'll tell you what, this would be continuous everywhere if that number was given as 4. If that was given as 4, then we just fill in that circle and say, we've got a continuous function. All right, this feels like a good moment to maybe stop the video and start it again, because trig is very different.